Hi, my name is Briana Strickland and I am a senior at Ursinus College. This past summer, I participated in the Triangle University's Nuclear Lab RAU program, where I worked with Dr. Richard Longland from NC State on reconstructing cross-sections in the Enge focal plane. In our Enge split-pole spectrograph, as particles exit the target chamber, they go through a magnet that bends these particles based on their incoming momentum and charge. This is shown in Figure 1. To get the differential cross-section measurements at different angles, we would have to move the whole spectrograph around the target chamber. In our old method, we would move the spectrograph some angle theta, count the number of particles, and then calculate the differential cross-section with the equation shown. Since our angle theta actually spans some range, we were essentially measuring the average cross-section for that span of thetas. This is shown in Figure 2 on the left. The goal of this project is to subdivide the particles entering the detector to extract the cross-sections in much finer detail for each theta span, which is shown in Figure 2 on the right. Our first step was to create a program to calculate these subdivided cross-sections. This program reads in position values from the front and back of the focal plane detector and calculates the angle at which the particles entered the detector, which is the angle phi, and this is shown in Figure 3. With these measurements, we can map the particles back to the scattering angle in the scattering chamber. Our next step was to test this method using well-known cross-sections in GM4 simulations. We started out with an isotropic cross-section simulation, which you can see on the top left of Figure 4. And then we used a linearly increasing cross-section shown on the top right of Figure 4. We used these simple cross-sections to characterize the capabilities and limitations of the ray tracing method. On both the isotropic and linear cross-sections, you can see that the data drops on the ends of the theta spans. These dips were expected as a result of increased scattering. The bottom left image shows 5 consecutive GM4 runs following the linear cross-section where you can see the dips between each of the theta spans. So even though the theta range is 10 degrees, we can actually only reconstruct a range of 8 or 9 degrees, which we have shown on the bottom right. The last test was to simulate a realistic cross-section setting in GM4, shown in Figure 5. The black points that you see here are the cross-sections we measured using the old method, and the red points are what we can now measure with the new subdividing method. We ran both results through model fits using distorted wave-borne approximation elastic scattering models, shown in Figure 6. The fit of the average cross-section is on the left, and the fit of the subdivided cross-section is on the right. The green line is the fit line with the error band, and the orange line is the true parameters that we simulated in GM4. For the subdivided data, we see much more agreement than with the average data. You can barely see the green error band, which is really exciting. Thank you for watching.